The equations of two circles are C1 is x squared plus y squared minus 6x minus 10y plus 29 equals 0. C2 is the circle x squared plus y squared minus 2x minus 2y minus 43 equals 0. Write down the centre and radius length of each circle. Now, just as a reminder of the equation of a circle, the centre is called hk, the radius is r. By Pythagoras' theorem, we can show that any point xy on the circle satisfies this equation here. This just comes from Pythagoras. I've explained it in other videos. I won't explain it here. Now, we can expand this out, and we get x squared minus 2hx plus h squared plus y squared minus 2ky plus k squared equals r squared. We can then get into standard form. That means get 0 on the right hand side. And I'll write x squared and y squared next to each other. I'll write the x term then, that's minus 2hx. Then the y term, which is minus 2ky. Then the constant term, which consists of h squared plus k squared minus r squared. So all of this is the constant term. It does not involve x or y. xy is a point on the circle. xy varies. X and y are the variables. So, and h, k, and r are fixed. The center is fixed, the radius is fixed. So all of this is just one number. And we normally call that number c. And, you know, if we know what c is, we can work back to, and if we know what h and k are, we can work back to find r. The first thing I want to do is note what h and k are for the circle C1. Well, you can see that the coefficient of x is minus 2h, and the coefficient of x in circle C1 is minus 6. So minus 2h equals minus 6, h equals 3. We just divide by 2 and change the sign. We do something similar for getting k. K is the y coordinate of the center. Minus 2k is equal to minus 10. So k is, we just half 10 and change the sign. K is 5. So we found the center of the circle. The center of C1 is HK 3, 5. Of course, we do something similar for C2. I'll do C2 now. I won't write it down. We just get the coefficient of x and half it to get plus 1. That's the x value of the center, or that's h for circle C2. We get the coefficient of y, half it and change the sign, and that gives us k, or the y value of the center of circle C2. Now, what about the radii of these circles? I'll just work with equation C1 just to, well, I'll just, first of all, I'll get a formula. The formula comes from seeing that the constant at the end of the equation is equal to h squared plus k squared minus r squared. So the constants for these circles are plus 29 and minus 43. So I'll just write down this equation here. C, just the relationship between the constant, that's the number at the end of the equation of a circle, and the center and radius. And we can obviously turn this around to make r the subject because we want the radius. So we see that minus r squared is c minus h squared minus k squared, which means that r is equal to the square root of, well, we just change the signs here. I'll write h squared plus k squared first. H squared plus k squared minus c. Now you could just memorize this formula or look it up or whatever. I just prefer to work it out. So we can apply this formula to each circle in turn to find the radius. So let's look at circle C1. C is plus 29. It's nothing to do with C1 and C2, of course. C1 and C2 are the names of the circles. This constant is normally called C in the general equation of a circle. This part here is normally called C. So it's plus 29 for circle C1. So, and we can now calculate r. We just use this formula. Square root of h squared plus k squared. Well, h is 3, k is 5. So it's 3 squared plus 5 squared minus 29. So the radius is the square root of 5, if you work that out. And of course we do something similar over here. But for this circle, C is minus 43, H is 1, K is 1. So R is the square root of H squared plus K squared minus C. That's minus 43. So this is the square root of 45. Prove that the circles are touching. Now what does touching mean? Well, it means that the circles touch at just one point. Not at 2 points, but at just one point. So for example, these two circles are touching. We would say that these two circles are touching externally. But we could have two circles touching internally. We would have this situation here. So in this situation, two circles just touch at one point. The intersection of the two circles is a single point. This is internal touching. This one is external touching. So what is the condition for two circles to touch either externally or internally? Well, let's look at external touching first. If we take the centers of the two circles and draw a line through them, well, if the circles touch externally, that means at just one point. It is a fact that the line through the centers will actually pass through this point. And what about the distance between the two centers? Well, the distance between the two centers is actually the sum of the radii. So if the radius of this first circle is r1 and the radius of the second circle is r2, then this distance here is the distance between the centers will be r1 plus r2. So that will be the case if the circles touch externally. If the circles don't touch externally, then the distance between the centers will either be greater than the sum of the radii or less than the sum of the radii. Like if the two circles don't touch at all, the distance between the centers will be greater than the sum of the radii. If the circles are closer together, if they cross at 2 points, then the distance between the centers will be less than the sum of the radii. Now here's another situation. Let's take the centers of these two circles and let's consider the distance between the centers of them. Well, if we look at the distance from here all the way to here, so a line drawn through the centers of these two circles will actually intersect the two circles at their common point. That's a fact. So that's the green line. The green line is the radius of the larger circle, which I will call R2. I'll write that in green. And the radius of the smaller circle is this distance here, which I will call R1. So R2 is the distance from the center of the larger circle to the point of intersection of the two circles, and R1 is just this smaller distance here. It's the radius of the smaller circle. So what's the distance between the centers? I'll just do it here like this. Well, the distance between the centers is the distance from here to here minus this radius. So it's R2 minus R1. So if the circles touch internally, the distance between the centers is the larger radius minus the smaller radius. So what we're going to do is look at the distance between the centers of these two circles. So we want the distance between 3, 5 and 1, 1. Well, that's just the distance formula which comes from Pythagoras' theorem. We subtract the x values of the 2 points, square them, then we subtract the y values of the 2 points, square them. So this is the distance between the centers. This is just Pythagoras. The hypotenuse is the square root of the sum of the squares on the other two sides. So if you draw this out, you can draw it out and maybe see why it works. But anyway, it's just a distance formula. Root x2 minus x1 squared plus y2 minus y1 squared. So what we have in here is 2. 2 squared is 4. Here we have 4. 4 squared is 16. 4 plus 16 is 20. So that's the distance between the centers. And now let's look at the radii. Let's look at, say, the sum of the radii. Let's look at, say, R1 plus R2. The sum of the radii is root 5 plus root 45. How does that compare to root 20? Is it the same or different? Well, clearly it's greater than root 20. Root 45 is definitely greater than root 20. So the sum of the radii is not equal to the distance between the centres. That means the circles do not touch externally, so we can rule out this situation here. The other situation is internal touching. So that's R2 minus R1. If R2 minus R1 equals root 20, we have internal touching. So R2 is the larger radius, which is root 45. Larger minus the smaller one, root 5. Is this equal to root 20? Well, you can simply go to your calculator, but I'm just going to be awkward and write root 20, break down these surds. Root 20 is the same as root 4 times 5, which is root 4 by root 5, or 2 root 5. Root 45 can be written as root 5 times 9. 5 nines are 45, so that's root 5 by root 9, or 3 root 5. So I can write root 45 as 3 root 5. Just factorize 45 and you can take the square root sign over each factor. And then we subtract root 5. So here we have 3 root 5 minus 1 root 5. Well, that's just the same as 2 root 5. So R2 minus R1 equals the distance between the centres of the circle. So the circles must look like this situation here. The circles touch internally at one point. Verify that 4, 7 is the point that they have in common. Well, that means that 4, 7 must be on both circles. So if a point is on a circle, it must satisfy the equation of the circle. After all, that's the meaning of the equation of a circle. So we just need to see if 4, 7 satisfies both equations. So we just plug 4 in for x and 7 in for y. So you can quite easily verify yourself that these expressions both work out to 0, which means that 4, 7 satisfies the equations of both circles, which means that 4, 7 must be on both circles, which means that 4, 7 is the point of intersection of the two circles. Two circles touch internally, so the situation is something like that's a bad diagram, of course, but in the next part we want to find the equation of the common tangent. Common means the same tangent that's common to both circles, so we're talking about the tangent through the point 4, 7, of course. So how do we find the equation of this line? Well, one way to do this would be to look at the center of this smaller circle. Look at the line from the center of the smaller circle to the point of contact of the tangent. Now it's a fact that this line is perpendicular to the tangent, so we can use that fact to get the slope of the tangent. We get the slope of the line joining the center of this circle to 4, 7, or the center of the larger circle, because as a matter of fact these 3 points lie on this line. So we get the slope of this line. That's quite easy to do because we have the centers of the circles. We can use the center of either circle. Get the slope of this line, then invert it and change the sign to get the slope of the tangent. And with the slope and point of contact, we can find the equation of the tangent. So I will write down the center of one of these circles, say the top one. We just look at the coefficient of x, half it, change the sign. That's 3. Look at the coefficient of y, half it, change the sign. Actually, I'll use the other one, it's easier, because this one just has a center with integer values. We worked this out in a previous question, but I'm just doing it again here. To get h, or the x value of the center, we get half of minus 2 and change the sign as plus 1. We get half of this minus 2 and change the sign, we get 1. So 1, 1 is the center of one of the circles. And we get the slope of the line joining 1, 1 and 4, 7. So the slope of the line joining the center of one of these, I don't know which one it is, it doesn't matter, to this point, the slope of a radius, I'll just write down slope of radius, I'll just call it a radius, it's a radius of one of the circles, is got by subtracting the y values and dividing by the difference of the x values. So we have 7 minus 1 over 4 minus 1, or y2 minus y1 over x2 minus x1. So this is 6 over 3, which is 2. So that means that slope of tangent is minus a half. So we just take plus 2, invert it, and change the sign. Now we can get the equation of tangent. So that's going to be y minus y1, where y1 is the y value of a point on the tangent at 7, equals the slope of the tangent minus a half times x minus 4. We can tidy this up by multiplying both sides by 2. So we have 2y minus 14 equals, and multiply minus 1 into the right hand side. So we get minus x plus 4, and then we end up with 2y plus x minus 18 equals 0. As a check, you could plug the 0.47 into this equation. Plug 7 in for y, 2 7s are 14, 4 in for x, 14 plus 4 is 18, 18 minus 18 is 0. So 47 is indeed on this line. So we can be quite confident that this is correct. Okay, so that's the equation of the tangent. Now there is a very interesting other method for doing this. That method involves taking the equations of the two circles and simply subtracting them. So we take x squared, subtract x squared, that gives us 0. Y squared minus y squared is 0. Minus 6x minus minus 2x, that's the same as minus 6x plus 2x, which is minus 4x. Minus 10y minus minus 2y is minus 8y. 29 plus 43 is plus 72. 0 minus 0 is 0. We're allowed to do that. We're allowed to take an equation and subtract the same thing from both sides. So if we look at this top equation, what are we doing? Well, we're subtracting all of this thing here from this side, but we're subtracting the same thing from the right hand side, because all of this here is equal to 0. So if we subtract this from this, we must subtract the same thing from the other side. But this is equal to 0, so we're subtracting the same thing from both sides of the top equation. So what we get is a true equation. This is valid. We can simplify this by dividing across by plus 4. X plus 2y. 4 into 72 goes, well actually I've divided across by minus 4. 72 divided by minus 4 is minus 18. 0 divided by minus 4 is 0. So this equation is the same as the one we just got. Now why does this method work? Well, the point of contact of the two circles must satisfy the equations of the two circles. So it must satisfy the top equation and it must satisfy the bottom equation. And it turns out that if we subtract the equations, the point of contact will satisfy the resulting equation. And the resulting equation is the equation of a straight line. It's linear. The x squared and y squared terms cancel out. So the point of contact satisfies this equation as well. I'll explain that in a little bit more detail in a minute. But for now, we know it's true that the point of contact satisfies this equation. It's a line, so the point of contact must be on this line. So we're talking about a line that passes through the point 47. Now to explain what I just did more fully, and this, I will let x1, y1 be the point of intersection of the two circles. Now everything I'm going to do next is an aside, so you can ignore it if you like, but I just want to give a full justification for the method that I used to get the common tangent to the two circles. Let's suppose x1, y1 is the point of intersection of the two circles. Then x1, y1 must satisfy the equations of the two circles. So in other words, if you plug the point of intersection into this first equation, you will get 0. So you will have that x1 squared plus y1 squared minus 6x1 minus 10y1 plus 29 will equal 0. Okay, so all of this here will equal 0. Now, you can imagine subtracting the second circle, but plug x1, y1 into the second circle. x1, y1 also satisfies the second circle because it's the point of intersection of it. I won't put equals 0. I'll just say that this bit is equal to 0 because the point of intersection is on this circle. So this has to work out to 0. So we have 0 minus 0, so the whole thing is 0. So we see that the point of intersection satisfies all of this equation if we put all of this equal to 0. But of course these cancel out. And we end up getting this here, as you saw already, x1 plus 2y1 minus 18 equals 0. So we've ended up showing that if x1, y1 satisfies the equations of both circles, in other words, if it's a point of intersection, then by combining these, by subtracting these, we get a 0, and everything simplifies down to this linear equation. We see that x1, y1 satisfies this linear equation. It satisfies the equation x plus 2y minus 18 equals 0. It's important to realize that any other point on the circle, any other point on, say, one of the circles that's not a point of intersection will not satisfy this, because it'll make one of them 0, but the other one will not be 0. So for example, suppose we take this point here. If we were to plug this point into all of this equation, well, one of these would be 0, but the other one would not be 0. So we'd have 0 minus some non-zero quantity. So we will not get 0 if we're talking about any other point, either on the large circle or the small circle. It's only for the point of intersection that we will have 0 minus 0, and that'll definitely get a 0. So this line here must only pass through one point on the circles, so it must be the point of intersection. Of course, it's possible that the circles could intersect at 2 points, and in that case we would have a common chord. We would have a line passing through the 2 points of intersection of the circles.